So what we're going to aim to do today is to make a kind of solar system simulator, which is kind of a toy, kind of a game, kind of something in between. And the way that this will work is, as a most basic thing, I want to be able to kind of place some planets down here, and then some other planets, and kind of give these like a speed, and then have them like continue into like orbit, stuff like that. So we'll be able to place planets down, give them like their speed and direction, and then they'll follow the kind of rules of gravity to kind of orbit around. You know, maybe we'd even have like a moon, which is going to orbit around this thing and kind of follow it around its own orbit. So that's kind of what I want to make as a baseline. What would also be really cool, if you ever played Kerbal Space Program, is to be able to have a little rocket ship and to be able to actually like fly that around. So, you know, maybe our ship's like here and it's on like this kind of trajectory. I want to be able to then like thrust the ship and have it show me the effect like on the orbit. Yeah. And the way this is going to work is it's going to be some basic like physics, gravity type simulation stuff. Yeah, so first of all I'm going to export this background into the data folder of our project. So I'm just going to call that Starfield. Then I've already looked up some images of some cool pixel art images of planets and rocket ships. These are from opengameart.org. So I will include all of these links in the code if you want to grab these yourselves, but this is a really nice site to get free open source licensed stuff that you can use without worrying about copyright and so on. So we have these planets, which we'll steal some from, and some of these ships, which I want to kind of steal as well. Yeah, it should be fun. Like, best case, this is a little like Kerbal Space Program style toy, but in the simplest case, it's a little simulator that just kind of runs by itself. I feel like this is a common little project to do. There's some interesting aspects to it. First of all, I want to make the background transparent here, and I'm just going to like crop out some of these planets. Into their own images. There's one. This kind of looks like the sun. That'll be useful. Let's do one more for now, and we can always pull more out later on and add asteroids and all that other cool stuff. So, let's make this one bigger. This is going to be the sun. Now the sun's not technically a planet, but I kind of want to name these consistently. Kind of Earth-like. It's kind of like a Jupiter-y planet. I don't know what we'll call it. I'll just call it the orange planet. That will do. Okay, next step is just to get these things loaded in. I'm going to make the window the same size as this image, I think, which is 1536 by 864. I think I cropped this to a weird size, but that's fine. Six. If you ever have any questions, by the way, or anything doesn't make sense, or you want me to clarify anything, then I'm totally happy to do that. And I'll try and keep an eye on the chat. Our background image. I will end up refactoring this later, but for now I just want to get like one sun and one planet going, and then we'll do the other stuff later. Ultimately, I want to be able to like scroll through different planets and place them down and drag them around and stuff like that. For now, I'm going to start off by like hard coding some stuff, and we'll kind of make it more flexible later on. Load our star field. Load our sun. Load our planet. Okay. So again, if you're not used to the processing framework, it's very, very simple. Except I've forgotten how to construct a P image. That's weird. Right. Yep. Yeah, sorry. So processing has this setup function which runs once at the start of the program, and it has this draw function which it runs over and over again. So for the draw, the first thing I want to do is to draw the background image. When you draw it, kind of you're drawing it, it's specifying the position of the top left corner of the image, which in this case we want to kind of line up with the window. So that should be all we need to do. Cool. So we have our star field here. It mostly fits on stream. Cool. Next, I feel like straight away I'm going to go straight into adding. I'm going to call it a planet. It's maybe more like a body or something. Could be a moon. Let's go. Should I call it something else? Okay, one thing that annoys me in this processing editor is I can't remove or rename this tab. Okay, I can like that. Call it a body. I feel like that's a more sciencey term. So what does a body need to have? Probably needs a mass. Probably needs a position. Probably needs also a speed or a velocity. When you create one of these, you probably want to tell it where it is and tell it all of these things, to be honest. It needs some initial velocity, which may be 0. So when it's constructed, these things get passed in, we want to save them off to these internal fields here. Then I feel like I want to give it... Okay, so I'm going to do this the wrong way first, and if anyone realizes what I'm doing wrong in terms of like physics, then please shout out, but we will discuss this and fix this afterwards. So when this thing updates, we need to apply gravity. What the hell is gravity? So probably an overly simplistic way to think about it, but gravity is a force which attracts things together. Let's bring up the Wikipedia definition. Okay, that's what I'm looking for. So our old friend Isaac Newton figured out that when you have two objects, they kind of apply a force onto each other, and that force is dependent on how far away they are. That's what this term here, it's called the radius, but it's kind of the distance and the mass of the object. So the heavier an object is, the more gravitational pull it applies to other things. That makes sense. The sun's like heavy, it's got a strong gravitational pull. You or I are not as heavy as the sun, but nevertheless we have a little small gravitational pull. And there's a kind of constant in there, and that kind of creates a force. So if we have two objects, we have object A, we have object B, then this distance between them is r, just a distance, and then A has a mass and B has a mass, so the amount of force is equal to the masses multiplied together. Let's call it A mass times by B mass, and then that's all divided by the square of the radius or the square of the distance. The cool thing here is that this F is the same for both of these, right? So the force that A is applying on B is exactly the same or exactly equal and opposite to the force that B is applying on A. So, you know, yeah, because the masses are kind of multiplied together and this force is applied to both of them. Which means that the force which the sun applies on me gravitationally is the same force that I'm kind of applying on the sun, except I'm much easier to move than the sun is. If you think about how this actually then causes stuff to move, we're back to another classic one of Newton's formula, which is F equals ma, where m is the mass and a is the acceleration. You can rewrite this to be the acceleration is equal to the force divided by the mass, which kind of makes sense, right? Like if I apply a certain force to something, if it weighs twice, if it's got twice as much mass, if it's twice as heavy, then I'm going to have less of an effect on actually accelerating it, and in fact I'll have like half the effect. And when you combine these together, you find that the m's kind of cancel out, right? So the force on A is equal to this, and the force of B is equal to this, but the acceleration on A ultimately gets divided by A's mass, and the acceleration on B ultimately gets divided by B's mass. So it kind of cancels out these terms, which means that the lighter thing moves a lot, while the heavier thing kind of moves less. Hopefully that made sense. Maybe that's kind of overcomplicated. It's actually pretty easy to implement code-wise. This is going to be a super naive way to do it, but it should work for us. And another key thing to realize is that everything kind of in the universe is applying a gravitational force on everything else. I think it's kind of limited by the speed of light in a sense, but if there are little other particles kind of around here, if there are other bodies, all of them are applying some force on A. So the total effective gravity on A is kind of, you know, some attraction towards this thing, some attraction towards this thing, some attraction towards B, some attraction towards some other thing there. So we kind of have to accumulate the force of like everything around us. One way to do this is to say let's make a new vector to kind of accumulate this acceleration. So it's complaining because it doesn't know what a list is, so I'm just importing the kind of standard utility Java package, which will kind of include that. Then all we want to do is kind of say, let's go over kind of need to figure out the gravitational attraction from each of these bodies. Of course, this list will probably contain, if we're Earth, then this list will contain the Sun and Earth right now, so we kind of want to skip over the case where we don't want to have a planet or a body apply gravity to itself. That'd be weird. The distance would be 0, we'd get divided by 0, it would all go crazy. So what is the gravity force? We can go straight back to our regular formula here. And it's as simple as saying dot multiplied by squared, where r is the distance. Oh, this is convenient actually that it's r squared, because part of the process of finding the distance between 2 points normally involves finding the square distance and then square rooting it just through Pythagoras, but we can kind of avoid having to do that. Except there's no square distance thing here. You know what, I'm just going to do this kind of manually, in fact. No, I won't. Okay. So to find a vector, a line like this going from one to the other, we can just take actually, it doesn't matter which way around we do it because we're just finding the length, but technically the vector pointing towards B is calculated like this. And the distance squared is just going to be there's a handy function here which will give us the square distance right off the bat. So we can just divide by that. Then all we need to do is say, okay, so that's the force, right, that B is pulling us to it with. The acceleration is going to be that force divided by our mass. So how do we do this? Okay, so in fact we can do something quite simple here. We can say let me draw something else out here. So we've already got, let's say now this is A and this is B. We've already got this vector to B. All we need to do now is kind of scale this down to whatever that force is, right? Hopefully that makes sense. See, the thing here is that this gravitational force is just a number, when actually we need this to be a vector. Take a vector and we can add to the B. Okay, this should do what we need. So we've already got the direct vector pointed to B. We set its length to be equal to the force, which kind of depends on our distance and the mass and stuff like that. Just divide by our mass there. Then we add that onto the acceleration. So what we've done here is we've kind of accumulated the forces and acceleration from all of these things which are affecting us gravitationally. And then what we want to do is to add that onto our velocity, right? So I would like to think of this stack of things in physics where you have the position of something, which is kind of influenced by its velocity or its speed. So its position changes over time based on its velocity or its speed. And then its velocity changes over time in accordance with acceleration. So there's this kind of chain of things. Something else we will need, though, is some sense of like how long has passed since the last update, because all of this, velocity is something per second, a speed, an acceleration is something per second, so we need this like time term. So we're also going to need to pass in what we normally call delta time, which is basically how many seconds have passed. I'm just going to name it seconds so it's more obvious. How many seconds have passed since the last kind of update? And then all we do is we use this to, so this acceleration we got will be like a per second value. So as this affects velocity, you kind of want to scale it by that. I remember what the, okay. Okay, we can just do it like this. So what I'm kind of umming and ahhing about here is we're using some of these operations which actually modify the original vector versus something like this which kind of keeps it in place. Maybe it's a bad instinct, but I have an instinct to avoid creating new vectors like this will possible. It totally should not be a concern here. The thing is, you basically need to be careful that you don't, if you're doing something which kind of corrupts something, so this acceleration now becomes like acceleration per scaled by the number of seconds, and if we then wanted to use it again, we'd have to remember that. So you kind of have to be careful. Same here, right? Like this, I could have got a new vector, which is this scaled version of vector to be, but since I never use this vector to be again, I'm just going to scale it in place and use it kind of directly. Cool, but I believe this should work. So now the velocity's been updated, then we also need to update the position in a very similar way. So we're going to add, so this time I'm not going to just say velocity dot multiplied by time interval, because this will work the first time around, but then the velocity needs to be maintained for the next update, and it will effectively get kind of corrupted by this. So I probably do in fact want to say, let's multiply this by that, so leaving the original velocity untouched. Cool. That's how we update this thing. Let's give it some like visual stuff as well. So we can ultimately draw this. I can also tell I've been using Go because I'm naming stuff in capital letters. So when we draw this thing, we're just going to use the built-in image function to draw the image at the position. The one issue is that this will draw our little planet image kind of anchored to the top left, when actually we kind of want to draw it anchored to the center. So all we need to do is say image mode center to do that. And then something which always trips me up is that means we then need to make sure for this one we set it to corner. The reason is that image mode carries over to the next call to this image function. So if we like drew a planet down here and then loop back around, then we would start drawing the background like pinned to its center, which is absolutely not what we want. Okay, so let's kind of create an array of these planets, I think. Okay, let's put some stuff in here. It might be nice to give these a name so we can ultimately like label them later. For whatever reason, my instinct is to logically separate this like physics stuff with like the more like visual stuff which doesn't really relate to the physics down there. So it at this position. Okay, so the first thing is the mass. What the scale is for this mass is like kind of arbitrary. I'll just call it 1 for now. So that's its position. Give it an initial velocity. Let's give it a an image. This is an interesting thing, so we need to know how much time has passed since the last run. That's something we've done on pretty much every stream, and I'm pretty much actually going to borrow the bit of standard code we used to do that. Yeah, so if we want to know how much time has passed between the last frames so we can make the physics work properly, the way to do that is like this. What we're doing here is we're capturing this will return the current time. Let's pull this out. So take the current time. We work out how much time has elapsed. So we take the current time minus the previous time. Seconds elapsed, it's just dividing that by 1,000 because 1,000 milliseconds in a second. And then we kind of remember this time so the next time around we can calculate the difference again. So in here we want to pass in seconds elapsed. And we want to give it a whole list of bodies so it can do its kind of gravitational stuff against them all. So right now that does not work. See where this gets us. Nowhere in particular. Oh, okay, we're not actually drawing this. That would help. Cool. So we have a planet. The planet is floating around happily. Okay, anyone who's done any physicsy stuff, there are a couple of glaring issues with this. But first of all, let me add one more planet so we can maybe try and get something orbiting something. So let's think about this, right? If we want something orbiting the sun, we need to create the sun. It needs to be real heavy. Like, we don't want it to move hardly at all. I think technically, like, when we orbit the sun is like slightly wobbling kind of in reaction to our movement, but it's like barely perceptible, so you'll see. So we have the sun, which needs a high mass, we need us with a low mass, and we should be going, if you're going to be doing a clean orbit, it means we should be moving, say if we're here, we should be going like exactly down or exactly up, and then the gravity should cause us to like curve around as we would expect. So let's figure out what these positions might look like. At the sun first. So let's put this at 500, 400. We definitely do not want it moving. Don't know how high this is going to need to be. We might add something in for like locking this so it's like truly static and doesn't move at all, even though that's not actually like physically accurate, but we shall see. The sun, then we want the planet to be, these comments are kind of redundant, I can see the label right here anyway. So I want this to be, say, like off to the side, but the same like vertical position, and I want it to be going, say, straight down, for example. We should see. And what we're going to need to do probably is fiddle with this to make sure if this is going too slow, then it's going to get sucked into the sun. And this is what happens in real like space physics, right? Like if I'm in this position, I need to be going fast enough this way. If I'm going too slow, I'll go here. If I'm going a bit faster, I'll go here. If I'm going just the right speed, then I'll end up in a stable orbit. And you can calculate what that speed is with another bit of math, but it's kind of going to be more trial and error here, I think. Let's have a look at this. Okay, going somewhere. See if we can amp this up a bit. This is on its side. Yeah, so some of the planets are weird, right? They're in like a weird arrangement. Oh, okay. So we just got catapulted out into space. We just got sucked into the sun, burnt to a crisp, and catapulted out. So clearly that sun is a bit too heavy. Let's try it a little bit lighter. Also, we're going super slow here, right? So I feel like we should be going faster, maybe put us a little bit closer. Okay, so there are a few issues here, mostly to do with, I actually call it the stability of our little physics simulation here. Does anyone have any thoughts on what the issue might be? So the first thing is that when the program first runs, the first couple of frames it's like kind of slow and janky, which means that this number that gets passed in is like super high. So for a more accurate physics simulation, what we probably actually want to do is do what's called like a fixed time step. So let's say 1/100th of a second here. So despite what I said here, we kind of almost want to ignore that and just do this smaller update. So that even if our computer's frame rate is faster or slower, the simulation kind of runs at a consistent step. And there's other things we can do around this. Let's up the speed a bit. Tweak these. Okay, we got a kind of sort of orbit going on here. So clearly we got a bit sucked in there, so we maybe weren't going fast enough, so we can now start increasing the speed till we get something that seems stable. Almost there, almost there. Nice. Okay, cool. This looks good to me. I kind of want to add trails to this straight away, right? Like I feel like that's a nice thing to do. So I think what I want to do here is have kind of keep a list going of my previous positions. Maybe I'll update that here. So I need to be careful. If I just add our position in, then it'll be the same actual vector, and it will be, even though I add them to this list, the old values will keep getting updated along with the new ones. So I kind of need to copy the position. That work? Does it have a copy? Okay, it has a copy function for us. There's a couple of common ways to like sort of clone something. Often they'll say if you just pass something into its own constructor, it creates a copy. That looks like the way they opted in this particular framework is to give you like a dot copy method. And then let's try just draw a little dot at each of the old positions. Set the kind of color of this. Just make it red. Okay. Cool. So now we have a little spirography thing, and it seems like we do indeed have a stable orbit for this planet. Add another planet in here, shall we? Okay, so there's a couple of issues actually. One is that this list is going to get bigger and bigger forever, so I feel like we kind of would like to have some limit to that. So something like this. And then we can say something like if make a constant for this. Let's take the last 100 positions. We should have a few more than that. 255 is a nice magic number. Cool. So let's add another planet or two. Put this one out to the other side. Get faster, see how that goes. Can't see that. Oh, of course. Seems like it's going too fast and it's flying away. Yeah, I was kind of messing up the relationship there. So basically, the closer you are, the faster you need to be going to avoid getting in. Right? It's like if you swing something around on a rope, then as you bring it in closer to you, it kind of like starts slow and then like winds up really fast. So it's kind of the same for these things, where if it's if it's like far away, it needs to be going slower in order to stay in an orbit, but if it's close, it needs to be going relatively faster to avoid getting sucked in. Cool, so we now have these two things. So in terms of our physics simulation, there are some issues here which may cause this to go crazy and blow up. The most obvious one here is to do with how we apply these updates. So if we look at this code here, right, so we've made it somewhat or considerably better by having like a fixed update length, so we're less sensitive to like this frame rate of the program. Probably if I removed that, we would see some jankiness and stuff maybe exploding. Let's take a look. Yeah. Probably because the first like frame is like super long, but even so, yeah, it's kind of all over the place. There are ways, in fact, to have a balance between these where we do multiple updates until we've done enough to like fill this time, but like the interval between them is always the same. You know what, since we're improving the simulation accuracy, let's actually go and do that. So then what we're going to do, that's the seconds elapsed. I'm going to say okay, what are we doing here? So what's happening is that on different frames of this thing, so our frames are not going to run at consistent speed, right? Like maybe one takes this amount of time, maybe one takes this, maybe the next one is slower and faster. But we want like a more regular like update kind of tick for these things with like equal spacing. So what we're doing here is the first time around, we're going to say, okay, we've got like this stretch of time, which we need to kind of do simulation for. And then we'll be able to do these little fixed updates. We'll be able to do this one, this one, this one, this one, this one, this one, this one. And then there's still like a partial update, which you weren't quite able to fit in. So what we'll do is that this little slice will be kind of carried over as a remainder, so that it can then be like accounted for. Next frame, you know, we'll do an update to get to this point and so on. That's kind of what it's doing. It's kind of accounting for like the carryover between frames here. So I'm going to change this to do while we've got, say our time step is like some fraction of a second, 20th of a second, while we've got at least that much time to catch up, we're going to do an update. I'm not going to do the draw because we don't want to draw things multiple times. In fact, let's move the draw out to its own little thing here. And then, so if you ever played with Unity, this is kind of similar to the fixed delta time in Unity, or like the fixed update function. Basically, if it's been a second since the last frame, we're still going to try and simulate like a second's worth of stuff, except we're always going to do it in slices of the same fixed size which we defined here. This should make the whole simulation way more consistent, right? So that if you run the program multiple times and your computers are running faster or slower at different times, the actual math and stuff is all going to be working on exactly the same interval each time, so we'll get a much more consistent thing going on. Yeah, so you see there, despite the fact that it was running more or less slowly, we got no issue there. The possible issue is if we can't simulate fast enough to keep up, then the thing will like totally tank, but you know, what are we going to do? Okay, so we've got that working. There's still a major issue with like how we're doing this physics update, and that issue is here. So what we're doing effectively here is and also here is that we're updating each planet or each body in turn. And at the end of this update, we change the position of this planet, right? So if we imagine we've got like 2 planets, we've got a planet here, another planet here, then effectively what's happening is we get into the update code for this planet. We go, okay, this thing's attracting us, we're going to move like slightly more in that direction. And then that's done. And now when this updates, it's going to say, okay, oh, this thing's attracting us, we're going to move like slightly in that direction. But there's a big issue here, right? Which is that when we did the update for this thing, it was looking at a new position for this, right? So maybe if I draw this another way, when we update this thing, it moves to here. And then when this thing updates, it's now looking at this new position, but we actually want it to look at the old position still. Because these things are kind of should theoretically be updating like at the same time, but because it's a computer, we kind of have to do them in a particular order. So we loop through it, we update one, and now the subsequent ones still update, and now they're kind of looking into the future and seeing the new position of this thing, which they really shouldn't be doing. So a simple way to account for this is to, rather than updating the positions, doing the calculations and updating the positions, what we can do is we can just go to this thing, we can update, we can work out what force should be applied to it, and then we work out what force should be applied to this, and then we do another pass at the end to actually update them to their new positions. Yeah, so the way I'm going to do that is I'm going to take the acceleration, and I'm basically going to split this into 2. So I'm going to say, or you know, yeah, update acceleration, or accumulate forces. Kind of makes sense. So what I'm going to do first is kind of set the acceleration to 0. Here I'm going to add onto that acceleration, but now this stuff I'm going to do as a separate stage. So I need to give this the delta. Yeah. So now it's a two-phase thing, and actually don't need the delta there. So basically what we do is we calculate the effects of all the forces, and then we're going to do this on all the planets, and then once they've worked out what gravity is doing to them, then we'll have a separate thing at the end where we actually update them. So what we're doing is 2 loops like this. Cool. So this will probably look mostly the same. And a lot of the time it won't have a visible effect. It kind of depends on exactly what kind of simulation you're doing, but these things with gravity and stuff, this is often super important because to get an orbit to like stay in a perfect circle and be consistent, it needs to be very kind of stable, and these little errors will cause stuff to like get subtly shifted and they'll go out of whack and end up flying around all over the place. So in any kind of scientifically accurate simulation it's possible, and even in this kind of toy simulation it's necessary if you want any kind of like actual stability to these things. Okay, so things are flying around. I feel like I kind of want them to be faster than this, so what's something I can just change as like a scale factor? Okay, cool. Kind of want to let this thing do an orbit. Okay, so what's the next step? So we note down some of the ways we could improve this. So it'd be kind of nice to have like a planet placement tool. It'd be kind of nice to be able to like save or load a whole little solar system setup. Be nice to have like manual control over something in here, like a spaceship or something. What else? What I think would be cool is like predicting the paths of stuff. Don't know why it is, but whenever I start my stream, my tablet starts doing this weird thing where it joins up lines. I think it's because my like FPS drops a bit and things in here kind of get janked up. Yeah, so what do we tackle first? Maybe we go for some kind of planet placement. Which means we could probably want like a little palette of possible planets. Prototypes. And let's add in. They don't need positions. So okay, so what I'm debating now is pulling out this information about mass and the image and stuff into a separate thing, which you can then have a kind of pool of. And then just having these refer to them in like a flyweight kind of thing. Let's put this here. Okay, so now we kind of have a way to. This is a bit janky, I don't super like this. But this is a way to create things from these prototypes, so I can just say something like create a new body. Cool. Kind of doing what we need there. So what I'd kind of like to do is to be able to place these down with the mouse and probably scroll through them with like the scroll wheel or something. Okay. Scroll or scrolled? Mouse wheel. Okay. Neither. Okay, and I think what I'd also like to do is say if we've got something selected, then I'm going to do very, very jankily. Draw this thing at the mouse position. Should hopefully mean you see these things. If I scroll the mouse, then I have a little thing here. I can scroll again. I can scroll through all of these things, or scroll to kind of having nothing in my hand. Cool. And I think what I can do then is okay. This little batch of stuff here is going to be the kind of state for like the user interface. What I kind of want to do is something like when the mouse is pressed, is it mouse down or is it mouse pressed? Mouse clicked, or is that when it's released? After it's been pressed and then released, so probably mouse pressed, so when the mouse is pressed, I kind of want to know the position where it was. So place position equals new with the mouse position. Yeah. And when the mouse is released, I'm going to say if I'm going to add something new here. So what I'm kind of using this for, this is kind of doing double duty here, which is fine here, but it's not the super cleanest approach. If this is null, then it means I'm not currently in the middle of placing something. But if it's got a position in it, it means that I'm kind of placing something. What I want to be able to do is to be able to click to choose a position and then drag to kind of set the initial speed of it, and then let go, and it will like ping off in the direction I've specified. Yeah, so kind of like a snooker game or a pool game or something, where I can like place something and set its velocity at the same time. So if we had a place position kind of queued up, and I've actually got a planet selected on the scroll wheel, then I'm going to add something new. So we know it's going to go, this is where it's going to be placed. The velocity is going to be new. So what we're doing here is basically saying, if I place like here and then I drag to this side, then its velocity is going to be whatever that difference is between where I started pressing and where I kind of drag to or where I released. And then all I want to do is say please dot add new body. It's going to be based on the prototype. It's going to start at place position, and it's going to have initial velocity. And we need to make sure we reset this to null. or some weird stuff will happen. You should need to press again to like start placing something. Okay. So I'm sure we can add some nicer UI to this, but now I can take this and I can drag over here. Nope. And then release. Okay. Yeah, that's not ideal. So first of all, if place position is null, then we're just going to previewing the position at the mouse. Otherwise, we actually want to draw it at that original position. And you know, why not even draw a line? From replacing it to here. Yeah, so I think this will have kind of the right effect we're looking for. Which is that. Oop. Nope, it's not good. You only want to do this if scroll through, I can position, I can start drawing a line, and then I can fire it off into space. And will it return? Who knows? Put something else here. Nice. And really screw stuff up by adding another sun. If I just click in place, it will effectively... Oh, oh dear. End of civilization, I think. Okay, so the one remaining... This is kind of cool. So the one remaining issue is that... not the one remaining issue. The main remaining issue is that we probably have a situation where these things can be so close that it kind of causes an issue. This distance, right? So I should probably specify like a minimum. So okay, so the issue we have is that in the real world, these planets, you know, they can only be like this close to each other, right? Like they can't be like literally overlapping because they have a physical shape to them and they'll kind of get in each other's way. But in the simulation, they can be right on top of each other, which means that their positions are effectively like right at the same point, which means the distance is effectively 0. And we divide by this distance, so we effectively divide by 0, and the force gets kind of crazy big. So probably what I want to do is just make sure that the distance squared, like no, is, you know, it's a bit arbitrary here, but it's never more than like 1 pixel. It means that if the things like come directly together, they won't blow up in too crazy of a way. Yeah. I'd be very surprised if we end up with like a stable arrangement here. I imagine these things are going to go all over the place. We've already flung off the orange planet. How about Earth? Earth is doing something. Yeah, this is kind of cool, actually. Okay, so I think what might be nice is if, for the sake of sanity, if we could tell a body that it's actually like fixed, like static. And all we'll do is just, if it's like fixed, then you won't do this update. It will still apply forces to other things, but it itself will not go anywhere. I kind of want to clean this up a bit. So we'll take the stuff from our prototype, set our new state. And when we create stuff up here, I can just say, yes, the sun is fixed. Place. False. So now we can have our sun here, we can throw another sun in, and it's fixed. It will interact with these planets somehow, but it won't totally screw stuff up. Throw this into the mix. Get a figure 8 orbit, that'd be cool. So when I was talking about stability, this is kind of relates to that, right? It's actually quite difficult to get planets set up in a system like this, especially when there's like more than a really simple thing, just doing plain circles around like one sun. But to actually get stuff to stay in a consistent pattern without getting flung out, like it's pretty hard essentially to do that. As we can see here, yeah, we lost that one. Like if you get the speed just right, then maybe you can make it happen. You know, there's a whole field of study around this. I guess it'd be like solutions to, yeah, right. So, or three-body problem probably makes more sense. So there are certain known solutions, like you can have three things like this, and they'll go around each other. And you know, people try and find new solutions to this all the time, but most of the setups you might create will just cause stuff to fly off and go crazy. This is cool. So you can probably find, you know, there'll be loads of papers which can define these things. You can probably find the parameters, like the positions and masses and velocities of these things, and then if we plug them into our thing, that'll be a good test of how accurate our simulation is, right? Like, probably this method we're using here is not sufficient to get the results you need. It's fine for like a game style simulation, but for like, this is not a rigorous mathematical thing right now. Might be nice to be able to delete stuff as well. So do something here where we say not a super clean way to do this. What I'm saying is find a vector between my mouse and the position of this thing, and if it's below a certain threshold, then I'm going to remember that I want to delete this. If I found something, okay. So now I should be able to do some stuff like, whoop. Deleting the sun and sending our little Earth off, try and recapture it. This is kind of fun. You can make a game out of this, I think.